Hello, calculus fans. Let's go ahead and prove that this series, the sum where n goes from 0 to infinity of 1 over n factorial, that this converges. One thing that we need to know is, what does 0 factorial mean? So by convention, 0 factorial is just equal to 1. There's some good reasons for that later on. Right now, let's just take that as a definition. All right, now we need a lemma in order to prove this. I haven't talked about lemmas before. A lemma is a theorem by itself, but it's not useful in and of itself. It is used to prove another theorem. The lemma that I want to prove is that for every n bigger than or equal to 1, n factorial is bigger than or equal to 2 to the n minus 1. All right, so to prove this, n factorial, which is 1 times 2 times 3 all the way up to n, I can replace all of these terms with 2, and we get something that's smaller. So those got replaced all with 2's. And then how many do we have together? Well, we have n to the minus 1 2's, so that product is 2 to the n minus 1. All right, so that now proves that n factorial is bigger than 2 to the n minus 1. So now what we're going to do is establish the convergence of the original series by showing two things: that the sequence of partial sums is increasing and that it's bounded above. So let's let S of n be the nth partial sum of the series. So that's 1 plus 1 over 1 factorial plus 1 over 2 factorial all the way down to 1 over n factorial. Now it's easy to see that S of n minus S of n minus 1 is equal to 1 over n factorial, and that's bigger than 0. So our sequence of partial sums is increasing. The last thing we're going to need to do is prove that S of n is bounded above our sequence of partial sums. So S of n looks like this. And according to our lemma, we can bound each piece. Remember that we proved that n factorial is bigger than 2 to the n minus 1. And so when we make that replacement on these terms here, we get the expression 1 plus 1/2 to the 0 power plus 1/2 to the first power plus 1/2 squared all the way down to 1/2 to the n minus 1. So this is by our lemma. And then this piece here is a finite geometric series. And earlier we came up with a formula for the sum of a finite geometric series. And if we put everything into that formula, this is what we get. The ratio in question here is 1/2. Now if we just drop this 1/2 to the nth power here, we still get something bigger because we're subtracting that off. So if we drop it, we get something bigger. And then that all works out to 3. So that gives us an upper bound on S of n. So according to the monotone sequence theorem, our sequence, S of n, is convergent. And remember that when we talk about the series, we are talking about a sequence of partial sums. And therefore, that series, n goes from 0 to infinity of 1 over n factorial, it is convergent. So we talked about two different series: the harmonic series, the 1 over n, and then the series that we're dealt with here, the sum of 1 over n factorial. The harmonic series was divergent, this one is convergent. And we'll be seeing both of these series again later on. In fact, this particular series, we'll be able to say something about what that series converges to. Right now, we haven't proven anything about that. We've only proven that the series converges. Okay, that's all for now.